There is nothing that needs to be held on to tonight. No sequence to follow, no argument to track. What follows is simply one material examined from its outermost surface inward, slowly, in genuine detail, with no particular urgency and nowhere else to be. Some people arrive at this kind of content after a day that asked a great deal of them, carrying the residue of too many decisions and too many voices, looking for something that occupies without requiring anything of them. Others come because a subject examined with genuine patience in real scientific depth has a quality that noise cannot replicate, not because it dulls the mind, but because it offers the one thing a busy day rarely does, a thought that has space around it. Either way, what follows does not need to be followed closely. It simply needs somewhere to be. There is a kind of attention that does not grip. It moves alongside what it observes rather than trying to capture it. That quality of attention suits what comes next, the slow, close examination of a material that most people encounter in the first quiet hour of every day, without ever once considering what it actually is, at the level where its character is decided. The room in question is a place most visitors never get to see. The walls are stone, and inside there are various glass jars. Some of those jars hold green beans, some hold lightly roasted beans, and some hold fully developed roasted beans. Each jar has a label on it, as if that label belongs to it alone. Right at the center of the room stands a warm amber lamp, doing everything it can to keep the darkness from taking over. And beneath that lamp sits a table, like a plant leaning toward the light to photosynthesize. This table has been prepared with care and patience. The air here is something to settle into. It carries a dry, faintly sweet earthiness, not the sharp, aromatic character of coffee as most people know it, but something quieter, more botanical, the smell of the material before it has become what heat will eventually make of it. The difference between what this material is and what it becomes is, at this stage, entirely invisible. Everything sitting in those jars is, in its current form, holding its chemistry intact. Nothing is released yet. The character is all still inside. Before we start, subscribing to the channel and liking this video will help more people discover this content. In a small open dish resting on the shelf closest to the lamp, there is a handful of green coffee seeds. Their color is not green the way fresh leaves are green. They are a little more faded, as if they are slowly getting ready to begin their work. Each seed carries a small crease on one of its faces. That crease tells of two seeds that once sat together inside the fruit. Now they sit quietly side by side, watching the world around them. Under close attention, the surface texture is visible, fine, slightly fibrous, with a dry smoothness that yields nothing to the finger other than a faint, chalky resistance. The skin of the seed is thin. It gives away nothing. This material is not technically a bean. The word has persisted through centuries of trade and habit, but what sits in that dish is a seed, specifically the pit of a small fruit roughly the size of a cranberry, called a coffee cherry. The fruit itself is real and edible, sweet and slightly fermented in character, with a thin layer of mucilage, a sticky and translucent coating surrounding the seed inside. What the world calls a coffee bean is the inner part of that fruit, separated from the surrounding pulp, dried, and kept in this still compressed form until something is done to it. Held in the palm, a handful of green seeds sits with a surprising solidity. They are dense in a way that seems out of proportion to their size, each one carrying its full moisture content, nothing yet driven off. The coffee plant, in most growing conditions, takes 3 to 4 years from planting before it produces its first fruit, a long preparation for something that most people encounter dissolved in water within minutes of the thought arising. The green beans in the dish weigh more than roasted beans of equivalent volume. This is not an impression, it is a measurable difference. Roasting drives off moisture and gas, and the bean loses somewhere between 12 and 22% of its starting weight, depending on how far the roast is taken, primarily as water vapor and carbon dioxide released from deep within its cellular tissue. The roasted bean is physically larger than the green one. It expands as its internal structure opens under heat, but it is noticeably lighter. What was compact and heavy becomes porous, riddled with the small channels and chambers left behind by the gases that escaped. A dark roasted bean held in the hand has the particular sensation of something that has undergone a significant physical event, denser in appearance than in weight, the way fired pottery feels lighter than its solidity suggests it should. The surface of a dark roasted bean carries a low, even sheen. The lipids, naturally occurring oils distributed throughout the bean's cellular tissue, migrate outward during extended roasting, arriving at the surface and leaving it with a finish that catches light differently than the matte surface of a lighter roast. Under a lamp, a fully developed dark roast looks almost lacquered, like polished wood with a very fine grain. A medium roast is drier, browner, without that surface film. A light roast is drier still, pale enough that the seam along the flat face is clearly visible as a slightly darker line against a cinnamon ground. The color running through all of those stages, the transformation from the pale interior of a green bean to the deep, graduated browns of a finished roast, is not produced by any pigment that existed in the original seed. It is chemistry made visible. The darkening begins in earnest at around 140 degrees Celsius, when a process involving the bean's amino acids and its naturally occurring sugars begins converting simple molecules into a wide family of new compounds that were not present before heat arrived. The color at any given stage is a record, a legible document of how much heat has been applied and for how long. Two beans roasted to an identical surface color by different temperature curves will have different compound profiles inside. The color confirms a degree. It does not describe a path. The smell above a freshly opened jar of green beans is entirely separate from the smell of roasted coffee. The difference is so complete it is almost difficult to connect them as the same material. The green bean offers something dry, faintly grassy with an undertone closer to raw grain or dried herbs than to anything most people would recognize as coffee. The aromatic compounds that define a roasted cup do not exist in the seed before roasting. They are created during the process, built from simpler molecules present in the green bean, transformed through chemistry into something entirely new. Current analysis has identified more than 1,000 distinct volatile aromatic compounds in roasted and brewed coffee, making it one of the most chemically complex food materials studied in detail. Green coffee, by current accounts, contains significantly fewer. Estimates in the available literature vary considerably depending on method and cultivar, with some analyses placing the figure below 100 and others reaching toward 300 or beyond, and many of those compounds are different in character from anything found in the roast. The roasting does not intensify what was already there. It produces something that was not there at all. That inventory of aromatic compounds, more than 1,000, and by most accounts not yet fully mapped, is one of the more striking numbers in food science. Wine, often cited as a model of aromatic complexity, contains a few hundred. Coffee's aromatic profile, at the level where chemistry can measure it, sits in a different category. New compounds continue to be identified, and the complete count remains an open question. For a material this extensively studied, that is an unusual and genuinely interesting position to be in. A brewed cup of coffee is approximately 98.75% water by weight. Everything that registers as flavor, aroma, color, and body, every distinction between one cup and another, everything that makes a particular cup different from one made 5 minutes earlier, is contained in that remaining fraction. The water brings its own chemistry to the encounter. The temperature it carries matters considerably. The window most widely considered optimal for extraction sits between 91 and 96 degrees Celsius, a range narrow enough that a few degrees in either direction produces a measurably different result in what the cup contains. The only place lit in the room is where that warm amber light falls. The rest of the room is dark. The jars do not stir in that darkness. They rest as if they can feel its stillness the way a person might. The walls pay no attention to the light falling on the table. They too seem to be a part of this calm and quiet. This stillness and calm is, for me, something irreplaceable. Quiet, peace, and the feeling of being somewhere safe. What the surface of this material offers, its color, its weight, the seam and smell, the particular oiliness of a finished dark roast, the dryness of the green, is the first of many layers at which coffee can be examined. Already at this outermost level, the chemistry has organized itself around a single measurable principle. Everything compressed, stable, and unactivated, the full inventory of compounds intact in their unaltered form, waiting only for the conditions that will convert them. The texture of the roasted bean, what holds that porous, expanded structure together, and why it fractures the way it does under a grinder's burr, is the next thing worth examining. The roasted coffee bean fractures cleanly. It does not bend, does not compress, does not deform the way softer materials do under pressure. It simply gives way at a threshold, and then it is in pieces. This is not a flaw in the structure.
It is a consequence of what roasting has done to the bean's internal architecture. The original green seed is a dense, continuous material, its cells tightly packed, its moisture content sitting at somewhere around 10 to 12% by weight, giving the whole structure a coherent solidity. Roasting drives that moisture out, drops the water content to somewhere between 2 and 5%, and simultaneously causes the cells to expand as the gases produced inside them push outward. What remains is a structure that is larger in volume than what it started as, but honeycombed with the spaces left behind by what escaped. The bean has expanded into a kind of rigid foam, strong enough to hold its shape on a shelf, brittle enough to shatter under a blade. It is the difference between a piece of solid wood and a dried wasp nest. Both have structure, but one has spent its density on mass, and the other has spent it on geometry.
When we grind a roasted coffee bean, we hear a crunchy, dry sound, but not an empty one. It is the sound of something organized, giving way in multiple places at once, as the cell walls fracture along their weakest points. The grinder pays no attention, simply doing its job for what comes next. And that sound reminds me that something worth drinking is on its way. That sound carries information about what it is working through. A denser bean, one taken to a lighter roast with more of its original cell wall mass intact, produces a slightly heavier tone, a more resistant quality to the crunch, as though the material is giving ground more reluctantly. A bean carried further into the roast, its cell walls thinned by longer heat exposure, fractures with less resistance, and the sound is marginally lighter, a shade closer to hollow. It is not dramatic, but it is there, and a grinder that has processed thousands of batches makes the difference audible to anyone paying attention to it. The fragments produced by that process vary in size depending on how far apart the burrs are set, but even at the finest grind settings, each particle retains its fundamental character, porous, oil-edged, and carrying on its surface the complete aromatic load that the roasting built into it. Ground coffee, held between thumb and finger, has a distinctive texture, not quite powdery, not quite gritty, but a combination of both depending on the grind size. A very fine grind, the kind used for espresso, feels close to powdered chalk at the surface of the fingers, with a smoothness that comes not from fineness alone, but from the oils coating each particle. Those oils, the lipids that migrated to the surface of the whole bean during roasting, are present on every fragment, however small. They give freshly ground coffee a faint cohesiveness, a slight tendency for particles to cling to each other and to dry surfaces. An hour later, the same grounds feel drier. The oxidation at those newly exposed surfaces is fast enough to be perceptible within the span of a single day. The fine particles losing surface volatiles at a rate that noticeably flattens the smell in an open container, and the aromatic compounds attached to them are escaping into the surrounding air at a rate proportional to how finely the coffee was ground. Grinding multiplies the surface area of the coffee by a factor of hundreds, and that increased exposure accelerates every interaction the grounds have with the environment around them. A coarser grind,
The kind used for a pour-over or a French press has a more openly textured feel. Individual particles are identifiable under close examination. Irregular fragments, some flatter, some more cuboid, most of them showing the porous internal structure of the bean in cross-section. The cut surfaces look almost sponge-like at small scales, the open cells of the expanded bean visible as tiny pits and channels running through the interior of each piece. Held in the palm for more than a few seconds, coarser grounds warm to skin temperature perceptibly faster than a whole bean would, the increased surface area giving the material less thermal resistance. The smell that rises in those first seconds of contact with skin is less sharp than the smell of a fine grind, more of the woody interior, less of the volatile surface compounds. The aroma profile shifted toward the structural rather than the aromatic. What the hand holds in a tablespoon of coarsely ground coffee is a collection of several hundred very small porous fragments, each one coated in oil, each one still releasing the carbon dioxide that was locked into the bean's structure during roasting. That release of carbon dioxide is the reason freshly roasted coffee produces a visible bloom when hot water first contacts the grounds. The water hits a bed of CO2-saturated particles, and the gas escapes rapidly upward through the water, causing the grounds to swell and rise in a dome of foam and turbulence that lasts approximately 30 to 45 seconds before subsiding. The physical sensation is subtle but specific. The grounds feel almost alive under that first contact, the surface moving and shifting as the gas pushes out from below. The CO2 concentration in freshly roasted whole beans is measurable and significant. Research into post-roast degassing has recorded values high enough that a sealed one-way valve on a bag of freshly roasted coffee will audibly hiss when pressed, the gas still actively seeking exit days after roasting. Roasters typically recommend allowing a week to 2 weeks between roasting and brewing, during which the bean's CO2 load gradually escapes on its own, because excessive gas during extraction can push the water away from the grounds before it has a chance to extract properly. The bloom in this reading is not decoration, it is residual energy from the roasting, making its last departure. The silver skin is worth examining separately because most people never notice it. It is a thin, papery membrane, technically called the spermaderm, the thin inner membrane of the coffee seed that clings to the surface of green beans and partially survives the roasting process. In lighter roasts, small translucent fragments of it remain attached to the bean's surface, particularly in the crease. In darker roasts, it has mostly detached, and it appears instead as the fine, papery chaff that collects in the chaff tray of a grinder or floats briefly in the air during roasting. It is extraordinarily light. A fragment of it placed on the palm lifts easily with a breath or with the warmth rising from the hand. Under close examination, it resolves into a layered fibrous structure, thin enough that light passes through it at the edges, coherent enough to hold its shape undisturbed, but too delicate to survive contact with anything moving faster than slow air. It is the last physical connection the seed has to the fruit it came from, and it survives the transformation into a roasted bean as something close to residue, present, delicate, and easy to overlook. Temperature response at the surface of a roasted bean is different from temperature response inside the cup. A whole roasted bean left on a cool stone surface for a few minutes will settle to the temperature of whatever it rests against without any particular resistance. The bean has low thermal mass. It is too light and too porous to hold warmth for long, unlike denser materials that retain heat in proportion to their mass. Ground coffee behaves similarly, but with an added dimension. The greatly increased surface area means it equilibrates with the surrounding air temperature faster than the whole bean does. A cup left to cool shows the opposite behavior. The ceramic holds warmth stubbornly, while the liquid inside loses it gradually at the surface, the top layer cooling first, while the deeper liquid stays warmer longer, the temperature gradient in the cup shifting slowly until the whole volume reaches equilibrium. That gradient is measurable. The top few millimeters of an open cup of coffee can register several degrees lower than the liquid at the base within minutes of pouring, the differential widening or narrowing depending on cup geometry, wall thickness, and ambient air movement. What the hand registers on the outside of a ceramic cup is always slightly less than what the liquid inside actually contains. The ceramic is a mild insulator, buffering the transfer. The weight of coffee at different stages of processing is worth holding in mind as a simple physical fact before moving any deeper into the chemistry. A green bean is noticeably denser than a roasted one. A handful of each, held in succession, makes the difference immediate. The green beans settle into the palm with a small, certain weight, the kind of quiet density that belongs to seeds that have evolved to survive and endure. The roasted beans, equal in number, feel almost buoyant by comparison. The weight loss during roasting, that 15 to 20% reduction, is entirely real, measurable on a scale, and physically perceptible in the hand. Something left during roasting.
The mass of water and gas that escaped is now in the air of the roasting room, and what remains behind is the dry, reorganized structure of the material, carrying everything the heat built into it. At commercial scale, across a drum roaster, processing dozens of kilograms per batch, that weight loss is tracked precisely between the green weight and the post-roast weight. It is a primary indicator of roast development, used alongside color measurement and first crack timing to determine when the bean has reached the target profile. Coffee grounds in contact with water gain weight rapidly. The grounds absorb approximately 2 grams of water for every gram of dry coffee, a ratio that means a standard dose of espresso grounds, typically around 18 to 20 grams, will absorb close to that weight again in water before extraction even begins in earnest. That absorbed water is not the extraction, it is the preparation for it. The wetting of the porous structure, the hydration of the soluble compounds at the surface of each particle, the opening of the material to the solvent that is about to move through it. What the grounds feel like after this contact, heavier, darker, clumped into a dense puck in an espresso basket or a loose, swollen bed in a pour-over filter, is the physical record of that first encounter. The material has accepted the water. The extraction has not yet begun in full. A puck of spent espresso grounds removed from the basket immediately after extraction has a particular character: firm, slightly cohesive,
still holding the compressed shape of the basket, dark and wet at the surface. Pressed against the palm, it breaks cleanly, the interior revealing a damp, granular structure that holds its form briefly before crumbling. The oils are spent. The soluble compounds have been pulled out by the pressurized water. What remains is mostly the insoluble structural material of the bean, the cellulose and hemicellulose of the cell walls, the insoluble fiber, the physical skeleton of what was once a living seed. The color is still dark brown, but the aromatic load is largely gone. The puck smells faintly of coffee, the way an empty jar smells of whatever it held, more record than presence. What holds the roasted bean structure together at the level below the visible, the molecular bonds between its cellular components, the way heat reorganized that architecture in the first place, is what the next layer of examination opens into.
Coffee is one of my favorite drinks, and making it for myself has always been a particular kind of pleasure. I like my coffee exactly as it is, bitter, nothing added, so making it has always felt like the easier part. Whenever I hear the word coffee, the first thing that comes to mind is, naturally, the color brown. But for some reason, a specific room always follows. A simple room, dark, with furniture that seems almost colorless in the low light. I imagine that room as a place where calm and quiet live. I picture it so still, without even trying, that I can say the ticking of a clock on the wall would be the loudest sound in it. But that ticking doesn't break the silence. If anything, it tells you just how quiet and peaceful the room really is. And that's before I even mention the smell that fills the room while the coffee is being made. I would want my home to smell like coffee all day. That smell reminds me of warm chocolate somehow. I even enjoy the way my hands smell of coffee after handling it. Making a cup I'm going to enjoy gives me as much pleasure as drinking it. What holds the expanded, porous structure of a roasted coffee bean together is not, at the visible level, immediately obvious. The bean looks fragile. It shatters cleanly. It crumbles under modest pressure from a thumbnail. And yet, a bag of roasted beans can be transported across an ocean, loaded into a hopper, transferred between containers multiple times, and arrive at the grinder in essentially the same form it left the roaster, intact enough to function, the cellular architecture preserved well enough to do its job. The cell walls of the coffee bean are composed primarily of cellulose and hemicellulose, the structural polymers that form the rigid scaffolding of most plant tissue. Cellulose is what gives plant cell walls their characteristic toughness, long, unbranched chains of glucose units arranged in parallel rows, bundled into fibers. Those fibers cross-linked in ways that make the whole assembly resistant to stretching, tearing, and compression. In a green coffee bean, this matrix is densely packed and moisture stabilized, the water content helping maintain flexibility and cohesion between layers. During roasting, that water leaves. The cellulose structure remains, but without moisture as a plasticizer, the cell walls become rigid and brittle. The same architecture that kept the seed intact while it was fresh becomes, after drying and heating, something more like fired ceramic, strong enough in compression but unwilling to bend. This is why the bean fractures the way it does. When a burr grinder applies shear force across a bean,
The cellulose network gives way at the interfaces between cells, the lines of least resistance, rather than tearing arbitrarily through the center of cell walls. The resulting fragments are not random. They tend to be fragments of former cells, with surfaces that map roughly onto where one cell ended and another began. At a fine enough scale, the particle edges are ragged in a structured way, following the geometry of the original tissue, even after the tissue has been reduced to powder. It is the same principle that governs how stone splits along its fault lines rather than across them. The material's inner architecture determines the shape of its failure. What also survives in the cell wall structure is something called galactomannan, a polysaccharide that exists in the endosperm of the green bean and contributes to the body of brewed coffee. It is a branched sugar chain, one long spine with shorter branches hanging off it at intervals, the molecular shape something like a fine-toothed comb lying flat. During roasting, some of the galactomannan is degraded by heat, converted into smaller fragments. The portion that survives into the brewed cup contributes to the characteristic thickness and mouthfeel of coffee, the quality that distinguishes a well-extracted cup from one that tastes thin and sharp. That sense of body is not from oil alone and not from dissolved solids alone. It is partly structural, carried by these large, partially degraded carbohydrate molecules that are too big to dissolve cleanly and too small to settle.
The physical hardness of a green coffee bean and a roasted bean of the same variety differ measurably. Green beans resist cutting. A knife pressed against one meets a surprising firm resistance, the kind of resistance that belongs to seeds evolved to withstand mechanical damage from the environment. A roasted bean from the same lot yields to the same knife with almost no resistance, surrendering at once, splitting cleanly. The interior surface of the split reveals something pale and open-grained, resembling nothing so much as a cross-section of balsa wood. Here the roasted bean simply yields. It offers no obstruction, raises no resistance, and comes apart with ease. The hardness has not increased during roasting. The structure has opened, the mass has left, and what remains is a rigid but hollow framework that carries only the memory of the original density. The crease along the flat face of the bean, the seam left by the two seeds sharing a single coffee cherry, is, at the structural level, a meaningful feature. The crease marks where the two seeds were in direct contact during development, pressing against each other as they expanded to fill the available space inside the fruit. The cells at the crease are oriented differently from the rest of the bean. They align with the surface of contact rather than with the interior tissue, and this difference in cell orientation means the crease is often the first line along which a bean fractures when force is applied. Press a coffee bean between two fingers and it will almost always fracture along the line where the two seeds once pressed against each other. The bean, it seems, knows and remembers how it was shaped. Coffee beans are not graded for hardness in the way that some gemstones or abrasives are, but the density of green beans, measured as the mass per volume of a specific quantity, is used as one marker of quality and altitude. Beans grown at higher elevations experience lower average temperatures and develop more slowly.
This slower development tends to produce a denser seed. More time at lower temperatures means the cell walls have longer to consolidate, and the sugars and acids inside have more time to accumulate. A denser green bean is generally considered to carry more complexity, more potential for the Maillard reaction to produce a wider range of flavor compounds during roasting, and more structural integrity during the roasting process itself.
The density figures used in the industry vary by origin and variety, but beans above approximately 700 grams per liter are typically considered high density, and beans from the highest altitude growing regions can reach above 800 grams per liter, a distinction measurable on a simple scale with a measured container, grounding what might otherwise seem like a subjective quality judgment in plain physical fact. The surface texture of a coffee bean at close range, examined under a magnifying glass rather than the naked eye, is not smooth. It is covered in a pattern of fine creases and shallow ridges that correspond to the cell walls just beneath the surface layer. Each ridge is the external trace of a cell wall running beneath the outer skin of the bean, the internal structure just barely visible through the surface layer. The spacing between ridges is not perfectly regular. It varies across the bean, reflecting the way cells grow to different sizes in different parts of the tissue. But the overall pattern has a consistency to it, the way wood grain has a consistency, not perfectly uniform, but clearly structured, clearly not random. There is a further detail worth the moment of attention. Coffee beans of different botanical varieties, Arabica and Robusta being the two most commercially significant, differ not just in the chemical composition of their seeds, but in their physical cell structure. Robusta beans tend to have a denser, more uniform cell arrangement in the endosperm. Arabica beans tend to have a looser arrangement, with more variation between regions of the seed. This structural difference is one of the factors that makes Robusta more forgiving during roasting. It is physically more consistent in how it responds to heat, and it holds up better to high temperatures without surface cracking. Arabica's less uniform cell structure is part of what makes it more sensitive. A few degrees of variation in the roaster can produce a noticeably different result in the cup. The physical architecture of the seed is not separate from the flavor. It is one of the mechanisms through which flavor is determined. The surface of a whole dark roasted bean, touched at room temperature, offers a tactile quality that is specific and not easily categorized. It sits between polished wood and dry stone. The oil at the surface fills in some of the fine creasing, giving the bean a sensation that is neither fully smooth nor fully rough. The oil is not evenly distributed. It pools slightly in the deeper creases, and thinner areas of the bean surface are drier, slightly more matte. This means the tactile experience changes with direction of movement. Stroking along the seam produces a different impression from stroking across it, the surface texture varying in that small, specific way that belongs to materials with genuine internal structure rather than those that have merely been coated to appear smooth. A lightly oiled surface that is also structurally irregular in this way has a quality closer to fine-grained leather than to glass or plastic. The sensation carries information about the thing beneath it.
There is one more layer worth locating before moving inward. Between the outer skin of the roasted bean and the endosperm beneath it sits a thin, papery membrane called the silver skin, a remnant of the seed coat that enclosed the developing bean inside the coffee cherry. In a green bean, the silver skin adheres tightly to the endosperm surface, filling the seam and the creased interior fold.
During roasting, the silver skin separates. It dries, loosens, and for the most part detaches from the bean surface entirely, becoming the chaff that collects in the chaff tray of a drum roaster during the roast. What remains on the bean after roasting is only a trace, most of it gone. A small amount clings inside the crease where the fold of the bean makes full detachment difficult. In the grinder, this residual silver skin breaks into fine, dry flakes that become part of the ground coffee. It contributes negligible flavor of its own, but its presence as a structural feature, a boundary layer between two tissue types, is part of what makes the bean's cross-section under a lens look organized rather than uniform. The structure of the bean's cell walls also determines how water moves through ground coffee during extraction. The open, porous cells left by roasting allow water to enter each particle from multiple directions simultaneously, not just from the outer surface inward, but through the channels and chambers left by the released gases. This multi-directional penetration means that even a relatively coarse grind exposes a large proportion of each particle's soluble content to the water, because the water is not limited to traveling inward from the outside edge. It finds its way through existing pathways. The extraction is, in part, following the architecture of the roasting, using the channels the CO2 left behind as the routes by which water will eventually carry everything soluble back out. What that extraction process involves at the molecular level, the specific compounds that dissolve, in what order and at what temperatures, is the layer that sits just below the physical structure. Coffee responds to heat in ways that can be tracked at every stage, and the behavior at each temperature threshold is distinct enough that experienced roasters use sound and time as their instruments alongside the thermometer, listening for specific events in the roaster the way a careful cook listens to a pan. The green bean placed in a roasting drum begins by absorbing heat without any dramatic response. For the first several minutes, the bean is simply warming, its moisture content still high enough to act as a heat sink, the water inside the cellular tissue absorbing thermal energy and slowing the temperature rise of the bean itself. This is similar to what happens when a wet cloth is placed near a heat source. The evaporation of water requires energy, so the cloth stays lower than a dry cloth would under the same conditions. The bean in the early stages of roasting is behaving the same way. It is wet enough that heat goes into water first, and the bean's core temperature lags behind the temperature of the roasting environment by a significant margin. The bean looks unchanged. On the inside, the water is beginning to move. As the core temperature of the bean rises through roughly 90 to 140 degrees Celsius, the bean transitions from an endothermic phase, absorbing heat, to the first stages of the exothermic reactions that will eventually produce roasted coffee. The cell walls begin to soften slightly as the remaining moisture distributes. the bean's color starts to shift away from green toward yellow, then tan, the first Maillard products beginning to form. The amino acids and reducing sugars inside the bean finding each other in the heat and beginning the long, complex chemistry that will produce the characteristic color and aroma of the roast. This color shift, which moves through a progression from hay yellow to pale cinnamon over a matter of minutes, is the first visible evidence of a chemistry that has been running invisibly for some time already. First crack arrives at approximately 196 degrees Celsius, and it is audible. The steam and carbon dioxide that have been building inside the bean's sealed cellular structure reach a pressure that the cell walls can no longer contain, and the walls fracture. When we roast coffee, the steam and CO2 building up inside the bean press harder and harder against the bean walls until they can't hold anymore, and they give. The crack that follows is light, hollow, not the sharp sound of splitting something solid the way you'd crack a firm walnut. This is softer, emptier. And when the beans go one after another, you get a quick sequence of quiet taps, gentle, almost muted. It is the moment the bean's structure changes fundamentally. What was sealed and pressurized becomes open and porous. The internal gas pathways formed by the ruptured cells now available for the carbon dioxide that will continue escaping over the following days. Between first and second crack, the bean is in a period of rapid transformation. The temperature is continuing to rise. The Maillard reaction is running at full speed, producing hundreds of new aromatic compounds in rapid succession. The Arabica's sucrose content, which started at roughly 6 to 9% of dry weight, is being broken down rapidly, the simple sugars feeding into caramelization chemistry at temperatures above around 170 degrees Celsius. Caramelization is not identical to the Maillard reaction. They run simultaneously, but through different mechanisms, using different molecular inputs. Maillard reactions require both amino acids and sugars. Caramelization requires only sugars and heat. Together, they produce the combined brown color and complex aroma of the roasted bean, and the balance between them shifts depending on the speed and temperature profile of the roast. A faster roast, moving through this temperature range quickly, produces a different ratio of Maillard to caramelization products than a slower roast, moving through the same temperatures at half the rate. The difference in outcome is detectable in the cup. Second crack arrives at approximately 224 degrees Celsius. The second crack is its own thing, different from the first, quieter, faster, softer, closer to slowly crumpling a stiff piece of paper. While that's happening, the oils trapped inside the bean are being pushed by the heat, moving toward the surface. Whatever CO2 is still left finds new exits, breaking through the cell walls one more time. The bean opens again, but deeper this time. At this point, the bean's internal structure is significantly more open than it was before roasting began, and the remaining solid mass is dominated by the insoluble cellulose framework and the aromatic compounds that have been built into the surface of that framework during the reaction cascade. Beyond second crack, the bean continues to darken. The aromatic compounds that were built during the Maillard and caramelization reactions begin to break down again under further heat,
a process of progressive pyrolysis, where the same heat that created complexity now destroys it. This is why very dark roasts tend to taste similar to each other. The individual aromatic profiles of different origins, which are detectable in lighter roasts, are progressively obliterated by the continued application of heat past the point where the compounds survive. What remains in a very dark roast is dominated by the simple aromatic products of cellulose degradation and the deep, bitter compounds that form during sustained high-temperature exposure. The temperature readings a roaster takes during this process are worth a moment of attention, because the number on the display is not the temperature of the bean, it is the temperature of the probe. A thermocouple mounted in a fixed position inside the drum, reading the air and the drum environment at that location. The bean temperature lags behind this reading, sometimes as much as 15 to 20 degrees Celsius in the early stages of roasting. Skilled roasters track the rate of rise, the speed at which the temperature changes per unit of time, as much as the temperature itself. A rate of rise that slows too quickly can indicate a stall, where the beans stop developing properly. One that stays too high carries the risk of tipping, scorching, or baking, terms for different kinds of thermal damage that affect flavor in specific, identifiable ways. The thermometer measures the environment. The roaster interprets what the bean is doing inside it. Temperature behavior does not end with the roast. A hot cup of brewed coffee loses heat at a rate determined by several interacting factors: the temperature differential between the liquid and the surrounding air, the surface area of the liquid exposed to that air, the thermal mass of the vessel containing it, and the presence or absence of a lid. A wide, shallow cup loses heat faster than a narrow, tall glass of identical volume. More surface area means more contact between the liquid and the air, and more contact means faster heat transfer in both directions. A ceramic cup with thick walls loses heat more slowly than a thin glass cup, because the ceramic's thermal mass is higher and it acts as an insulating buffer. A lid reduces heat loss to the order of 1/3 or more, primarily by trapping the humid air above the liquid and reducing evaporative cooling at the surface. The optimal temperature window for drinking brewed coffee, roughly between 55 and 70 degrees Celsius, is a relatively small target in the cooling curve of a freshly brewed cup, which typically exits the brewer at somewhere between 85 and 95 degrees Celsius. A cup without a lid in a typical room temperature environment passes through that drinking window in somewhere between 5 and 15 minutes, depending on the vessel and the volume. Outside that window, in both directions, the coffee is objectively different. Above 70 degrees, the heat itself interferes with the perception of certain aromatic compounds. The tongue's ability to detect some of the volatile aromatics is reduced at very high temperatures, and the perception of bitterness is enhanced. Below 55 degrees, the balance of perceived flavor shifts again. Acidity becomes more prominent. Some of the pleasant aromatic complexity begins to flatten as the volatile compounds slow their release into the air above the cup, and the oils that were in solution begin to separate slightly. Neither state is wrong. They are simply different expressions of the same chemistry, observed at different points on a single cooling curve. The thermal behavior of coffee during brewing is also relevant to what ends up in the cup. Hot water extracts different compounds from the coffee grounds at different rates. The most readily soluble compounds, acids, certain salts, some small aromatic molecules, dissolve quickly.
The more complex compounds, certain melanoidins, longer polysaccharides, heavier aromatic structures, require more heat and more time. Under-extraction, which tends to happen with water that is too cool or contact time that is too short, leaves the cup dominated by the first extracted compounds, often sour, thin, and unbalanced. Over-extraction, which happens with excessive heat, contact time, or both, adds too much of the compounds that come last, bitter, harsh, and heavy. The optimal extraction sits at a precise balance, and the temperature of the water is one of the most direct levers available for moving that balance in either direction. There is a further thermal phenomenon specific to espresso that is worth noting separately. The elevated pressure of espresso, conducted at 8 to 10 atmospheres of pressure, applied through a tightly packed puck of fine ground coffee, is capable of extracting certain compounds that regular hot water brewing at atmospheric pressure cannot reach efficiently. The elevated pressure, combined with water temperature held precisely at 91 to 96 degrees Celsius, drives the water into the puck with sufficient force to pull compounds from the internal cell surfaces of the grounds, surfaces that slower brewing methods might never fully contact. The crema that forms on the surface of a well-pulled espresso is one visible consequence of this. The high pressure causes dissolved CO2 to emerge rapidly as the pressurized water exits the puck and enters atmospheric conditions, forming a foam of protein-stabilized gas bubbles that floats on the surface. That thin layer of foam a lot of people love, it looks simple. It isn't. It's a compressed version of everything the bean was holding inside. The aroma rising from it is stronger and more layered than the liquid sitting just beneath. High pressure drives water straight through the grounds and pulls every aromatic compound along with it. And as that stream hits open air, the foam forms in under a second. Before you take a single sip, it's already there, waiting. What thermal processing makes visible, the conversion of green seed chemistry into the hundreds of compounds that define roasted coffee, is, at a finer level of examination, a story about molecular structure and molecular change. The chemistry inside a roasted coffee bean is not a collection of simple compounds sitting in solution. It is a dense, interacting network of molecules, some stable, some reactive, some volatile enough to be in the air above the cup before the cup is even lifted. And the interactions between them are what makes coffee's aromatic and flavor profile one of the most studied in food science. Caffeine is the compound most people name first, and it is worth beginning there because its chemistry is more precise than its reputation suggests. The molecule itself has a molecular weight of 194.19 grams per mole, a relatively small, compact structure built around a two-ring system called a xanthine base, with 3 methyl groups attached. This arrangement makes it moderately soluble in hot water, highly stable during roasting, and unusually resistant to thermal degradation. Caffeine survives the entire roasting process essentially intact. A light roast and a dark roast of the same bean contain approximately the same amount of caffeine by dry weight. The widespread belief that dark roasts are stronger in caffeine than light roasts is mostly a matter of volume.
Because dark roasting drives off more mass from the bean, a dark roast is physically lighter per bean than a light roast, so an equal weight of dark roast contains marginally more beans and marginally more caffeine. The difference is small and often overstated. What differs dramatically between roast levels is not caffeine, but everything else. Chlorogenic acids are among the most abundant active compounds in green coffee, making up somewhere between 6 and 10% of the green bean's dry weight. They are a family of esters, molecules formed from a combination of caffeic acid and quinic acid, and they carry significant antioxidant activity. In roasting, chlorogenic acids undergo substantial degradation. They break down through heat into their component parts. Caffeic acid and quinic acid separate, and quinic acid subsequently undergoes further reactions to form quinactylone compounds that contribute to the bitterness of dark roasts. The chlorogenic acid content of roasted coffee is considerably lower than in the green bean. Light roasts retain more, dark roasts retain substantially less. This means that the antioxidant profile of a cup of coffee shifts measurably with roast level, a fact that current nutritional research is still working through in terms of practical implications. The chemistry of any given cup is partly a function of how far the roaster chose to take it. Trigonylene is another alkaloid present in significant quantities in green coffee, around 1% of dry weight in Arabica, and it behaves very differently from caffeine during roasting. Unlike caffeine, trigonylene degrades readily under heat. As it breaks down, it produces a range of pyridine compounds that contribute to the aroma of roasted coffee, and it also generates niacin, which is a B vitamin. This means that the roasting process is not simply destroying trigonylene. It is converting it into other things, some of which become part of the aromatic profile of the cup. Light roasts retain more trigonylene. Dark roasts have converted more of it, producing higher concentrations of its breakdown products instead. The loss of one compound and the gain of another from the same molecular precursor is a fairly direct example of how roasting is less a process of degradation and more a process of conversion. The same heat that removes one molecule builds several others in its place. The Maillard reaction deserves more than a mention in passing because it is not a single reaction. It is a family of reactions, potentially hundreds of parallel chemical pathways running simultaneously, all sharing the same starting point, an amino acid and a reducing sugar in the presence of heat. The amino acids in coffee are numerous. The reducing sugars include glucose, fructose, and the breakdown products of sucrose. When heat drives these compounds together, the initial product is a molecule called an amidori compound, which then breaks down further into a cascade of more reactive intermediates. These intermediates react with each other and with other compounds in the bean to produce melanoidins, the large, brown, complex molecules that give roasted coffee much of its color and a significant portion of its body, as well as an enormous variety of smaller aromatic molecules. Pyrazines are among the most recognized of these, compounds with a nutty, roasted, earthy character that are produced specifically through Maillard pathways and are largely absent from the green bean. Furans, which carry a sweet, caramel-like character, are produced both through the Maillard reaction and through caramelization. Thiophene, which are sulfur-containing aromatic compounds, contribute to what some describe as a faint roasted meat character in certain coffees, a subtle undertone in the aromatic background that disappears with longer roasting as the compounds break down further. According to peer-reviewed food science research, the count of volatile aromatic compounds identified in roasted coffee stands above 1,000. That number continues to move. New analytical techniques, particularly advances in high-resolution gas chromatography and mass spectrometry, are capable of detecting compounds at concentrations so small that previous methods would have missed them entirely. Whether all of these compounds contribute meaningfully to the aromatic experience of a cup, or whether many of them are present in quantities too small to register in human perception, is a question that research is still working through. The threshold at which a given compound begins to influence what a nose or palate detects varies by several orders of magnitude from one molecule to another. Some aromatic compounds have sensory thresholds measured in parts per billion, detectable at extraordinary dilution. Others are present in the cup at much higher concentrations, but contribute relatively little to what is perceived because the perception threshold for that particular molecule is high. The relationship between concentration and perception is not linear. A compound present at twice the concentration of another may register as significantly less intense simply because the olfactory system is calibrated differently for each molecule. Water is the solvent that extracts all of this chemistry from the grounds and carries it into the cup. Its behavior is not chemically passive in this context. Water molecules are polar. They have a slightly positive region at each hydrogen atom and a slightly negative region at the oxygen atom, meaning the molecule as a whole has an uneven charge distribution. This polarity makes water an excellent solvent for other polar or charged molecules, which is why ionic compounds and acids dissolve readily in it. It makes water a less effective solvent for nonpolar molecules, which is why oils do not dissolve in water, but instead form emulsions, which are suspensions of tiny oil droplets held apart by the physical agitation of the brewing process. The lipids that contribute to the body of a cup of coffee are not truly dissolved. They are suspended, distributed through the water in microscopic droplets, small enough that the cup appears uniformly dark, but present as a separate phase at the molecular level. Two of the specific lipids worth identifying by name are cafestol and caweol, both diterpene alcohols, meaning their carbon skeletons are built from 4 isoprene units linked in a specific configuration. They are present in the waxy interior of the coffee bean at concentrations that vary by variety. Arabica contains both. Robusta contains cafestol, but negligible caweol. In a filtered cup, a French press, or a traditional boiled preparation, both compounds enter the brew freely. In paper-filtered coffee, they are largely retained in the filter along with the coarser oil droplets because paper traps particles and oils above a certain size. The body of an unfiltered cup and the cleaner texture of a filtered one are, at the molecular level, partly a story about whether these two specific diterpenes made it through. At the surface of each coffee particle during extraction, the sequence of what dissolves is somewhat predictable. Small, highly soluble molecules, tartaric acid, malic acid, certain small aromatic compounds, dissolve quickly and begin entering the water almost immediately on contact. Caffeine follows relatively quickly. It is moderately soluble and present in high enough concentration to enter solution efficiently. The larger, more complex molecules, melanoidins, galactomannins, long-chain polysaccharides, require more time and more heat to enter the water. This sequential extraction is one reason that both very short extraction times and very long ones tend to produce unbalanced cups. A very short extraction captures the first solubilized compounds before the later ones have had time to enter the water. A very long extraction captures everything, including compounds that, in quantity, turn the flavor harsh. The management of this sequence is the core problem that every brewing method addresses in its own way. One compound that plays a specific role in the sensory experience of coffee and whose mechanism of action is particularly clear is 2-furfuryl-thiol. It is present in roasted coffee at extremely low concentrations, parts per billion, and yet it is considered one of the key contributors to what is recognized as the characteristic smell of coffee. Its odor threshold is very low, meaning it registers with the olfactory system at concentrations where most other compounds would not be detectable. The compound is produced during roasting through a Maillard pathway and is highly volatile. It escapes into the air above the cup rapidly once the cup is poured. This explains why coffee's smell hits harder than its taste, because the compounds that produce the most intense aroma are also the ones that disappear the fastest. The moment you eagerly carry the cup over, before it has even reached the table, that most powerful scent has already started bleeding into the air. So by the time you pick it up, your nose has already taken the best of it. Finding that same thing in the taste simply isn't possible anymore. As we know, there is a difference between coffee's smell and its taste. And we can say this is also a difference in time, not just in intensity. From the moment we catch that first scent, the compounds are already mixing into the air and spreading through the room, as if impatient to explore their surroundings. By the time we actually taste it, we are meeting a different set of molecules entirely, heavier ones, slower-moving ones. So coffee's taste is not a fixed thing. It arrives in waves, the most fleeting ones first, the most persistent ones last. What holds these thousands of molecules in the relationships they have with each other, what governs which ones escape into the air and which stay in solution, which ones interact to produce new compounds and which pass through unchanged, is the deeper level of molecular bonding and intermolecular forces. Coffee changes after roasting, not in dramatic ways, not in ways that announce themselves on a particular morning, but measurably, consistently, in directions that move the cup in a single direction, away from what the roast produced and toward something simpler. The primary mechanism of deterioration in roasted coffee is oxidation. This is the same process, the slow reaction between organic compounds and the oxygen present in the surrounding air, that affects most complex organic materials over time. In coffee, it targets the volatile aromatic compounds most directly. These molecules, built during the Maillard reaction and caramelization at temperatures above 140 degrees Celsius, have reactive sites, specific bonds within their molecular structures that are vulnerable to attack by oxygen. When an oxygen molecule reaches one of these sites, it forms a bond with the carbon or sulfur atom there, converting the original compound into a different one. The new compound has different physical properties. Often it is less volatile and carries a different aroma, frequently described as flat, papery, or stale. The characteristic freshness of newly roasted coffee and the papery dullness of coffee that has been open for 3 weeks are the same process observed at different points on a timeline. The molecules that produce freshness have, one by one, been converted into molecules that do not. The rate of oxidation depends on several factors. Temperature is the most direct. Warmer storage accelerates the reaction, and cooler storage slows it. The surface area of the coffee is the second most important factor, which is why whole beans oxidize more slowly than ground coffee, and why the difference between the two is not slight. Grinding increases the surface area of a given mass of coffee by a factor of roughly several hundred, exposing that much more of the aromatic compound-bearing cell wall surface to the surrounding atmosphere. A bag of whole beans left open on a shelf will show perceptible flavor deterioration over a period of weeks. The same beans ground on the same day will show comparable deterioration within hours. This is not an opinion. It is the same chemistry running faster on a larger surface. Moisture is the third significant driver of staling in ground coffee. Coffee is hygroscopic. It pulls water from the surrounding air the way a dry cloth absorbs a spill, not rapidly, not dramatically, but steadily, without being asked. The water that accumulates on the surface of coffee grounds and within their porous structure accelerates oxidation by providing a medium through which reactive molecules can move more freely. It also initiates hydrolysis, the chemical breakdown of certain compounds through reaction with water, which degrades both aromatic molecules and some of the polysaccharides that contribute to the body of the brewed cup. Humidity is measurably worse for stored coffee than dry cold. A refrigerator with low humidity is preferable to a warm, humid kitchen counter, but the repeated opening of a refrigerator container, bringing the cold, relatively dry coffee into contact with the warmer, more humid kitchen air, causes condensation on the coffee grounds with each cycle, which introduces moisture directly. This is why specialty roasters typically recommend storing roasted coffee at room temperature in an airtight container in a cool and dry location, rather than in a refrigerator that is opened frequently. Freezing is a different matter. A sealed container of roasted coffee placed in a freezer at a stable temperature and not removed until it is ready for use can be held for several months without significant deterioration. The low temperature slows oxidation substantially. The frozen moisture cannot move or facilitate hydrolysis. Provided the container is genuinely airtight and the coffee is not repeatedly thawed and refrozen, each cycle of which introduces condensation on the grounds, the freezer is an effective long-term environment. The key condition is stability. One freeze, one thaw, then use. The chemistry of deterioration does not reverse on thawing, but it has been slowed for the storage period. A bean that has been held frozen at -18 degrees Celsius for 2 months emerges into room temperature, carrying essentially the same aromatic load it had when it went in. The oxidation clock paused. Carbon dioxide loss is a parallel process to oxidation, running simultaneously but through a different mechanism. As described earlier, Roasted coffee is saturated with CO2 produced during the roasting process, and this gas continues escaping after roasting through the open cell structure of the bean. The gas leaves through the pores of the bean's surface and, in a sealed bag, accumulates until the pressure inside the bag would exceed what the bag could hold, which is why specialty coffee bags have a one-way valve allowing CO2 to escape without admitting air. The valve itself is a small, layered disc, typically a few millimeters in diameter, bonded to the interior of the bag. It contains a membrane that flexes outward when internal pressure rises above a threshold, allowing gas to pass through a small channel to the outside, then reseats itself when the pressure drops. The membrane's behavior is passive and mechanical. No power, no moving parts beyond the membrane itself. Its function depends entirely on the pressure differential between the bag interior and the outside air. Roasters who package coffee within the first 24 hours after roasting face a practical problem. The CO2 emission rate is so high that even a functioning valve may struggle to release gas quickly enough to prevent the bag from distending. Some roasters address this by resting the coffee in open containers for a day before sealing. Others accept some distension as normal and calibrate the valve accordingly. In the weeks following roasting, CO2 emission slows progressively as the gas pressure inside the bean decreases. A bean that has been off roast for 2 weeks has released a significant portion of its original CO2 load. A bean at 4 weeks has released most of it. At 6 weeks, the remaining CO2 inside the bean is a small fraction of the original, and the bloom produced when hot water contacts the grounds is correspondingly smaller. This off-gassing has a practical consequence for extraction. A bean with a high internal CO2 load, very freshly roasted, can actually resist water penetration during brewing. The gas escaping outward through the porous cell structure physically competes with the water trying to penetrate inward. This is why very freshly roasted coffee, within the first day or two after roasting, can produce an under-extracted cup despite using the correct parameters. The CO2 is, in a sense, pushing the water away before it can do its work. The resting period most specialty roasters recommend, typically 7 to 14 days post-roast, is the period during which this gas load decreases to a level where extraction can proceed without interference. The bloom at the start of a pour-over is the remaining CO2 making its most rapid exit under the prompt of hot water contact. And a vigorous bloom on a bean at 10 days post-roast is a positive sign. Enough gas remains to indicate freshness, but the initial extraction resistance has dropped to a manageable level. The oils on the surface of a dark roasted bean also change over time. These lipids, caffeostol and caffeol being among the most studied, along with triglycerides and fatty acids, are vulnerable to oxidative rancidity. Rancidity in oils occurs when the reactive double bonds in unsaturated fatty acids are attacked by oxygen, producing peroxides that subsequently break down into shorter-chain volatile compounds, including aldehydes and ketones, that carry the flat, fatty, sometimes crayon-like smell associated with old coffee. The surface oils of a dark roasted bean, being directly exposed to the atmosphere, oxidize faster than the internal lipids. This is why the oily surface of a freshly dark roasted bean smells complex and aromatic, while the surface of the same variety at 6 weeks smells heavier and flatter, and at 3 months may carry a detectable rancid note that no amount of skilled brewing will compensate for. Green coffee does not deteriorate in the same way or on the same timeline as roasted coffee, and this difference is structural. The green bean's chemistry is not in the volatile, highly reactive state that roasting creates. The aromatic compounds that are so vulnerable to oxidation in roasted coffee do not yet exist in the green bean. They will be built by heat when roasting eventually occurs. What the green bean does experience over time is moisture-related, changes in water activity, possible mold growth in humid storage conditions, and the slow hydrolysis of chlorogenic acids and other ester-linked compounds. Well-stored green coffee can remain viable and produce a high-quality roast for 1 to 3 years from harvest. Some processed lots, stored under controlled conditions, have reportedly maintained quality for longer, though the evidence at the extreme end of this range is limited and not widely replicated under rigorous conditions.
Coffee does not get better over time the way some things do. Keeping coffee for a long time after roasting is not the right approach. For roasted coffee, there is only one direction, down. It never improves on its own. The chemistry that produces complexity in the cup is the chemistry most vulnerable to the environment. The compounds that were built at temperatures above 140 degrees Celsius through reactions requiring precise conditions are the ones that oxygen and moisture at room temperature work most efficiently to dismantle. There is no mechanism by which ordinary time and ordinary air restore what they have taken. The aromatic molecules that oxidation converts into flatter, heavier compounds do not convert back. The direction of the process is fixed, and the only meaningful variables are temperature, humidity, and how much surface area has been offered to the air. That those same compounds were built at all, the specific chain of events by which a green seed becomes something capable of producing over 1,000 distinct volatile molecules in a single roasting session, is a question that leads, at the deepest level of examination, into the molecular structure of the reactions themselves. At the level where chemistry becomes physics, where the behavior of molecules resolves into the behavior of atoms, and the behavior of atoms resolves into the behavior of electrons, coffee occupies an interesting position. Its molecular complexity, which is already extraordinary by the standards of food science, rests on a relatively small number of fundamental atomic interactions. The same bonding principles that govern the structure of water or salt or any other ordinary material govern the structure of every compound in the cup. The complexity is not in the rules, it is in how many things those rules have been applied to simultaneously in a very small space. Every aromatic compound in roasted coffee is an organic molecule, a structure built from carbon as its backbone. Carbon is the organizational center of these molecules for a specific reason. It forms 4 bonds, which is more than nitrogen's 3, oxygen's 2, or hydrogen's 1. And this bonding capacity allows carbon to build the branched, ringed, and chained structures that organic chemistry is made of. A caffeine molecule contains 8 carbon atoms, 10 hydrogen atoms,
4 nitrogen atoms, and 2 oxygen atoms. Each of those atoms is held to its neighbors by covalent bonds, the sharing of electron pairs between atoms. The specific arrangement of those bonds and the angles at which they sit relative to each other is what determines the molecule's three-dimensional shape, and the three-dimensional shape of the molecule is what determines how it interacts with an adenosine receptor in the brain, which is, ultimately, what caffeine's most discussed effect depends on.
Adenosine is a signaling molecule the brain accumulates during waking hours, binding progressively to specific receptors and producing, through that binding, a signal that the body interprets as fatigue. The caffeine molecule is structurally similar enough to adenosine that it can occupy the same receptor sites. It does not activate them, it simply sits in them, the way a key that fits a lock but cannot turn it will still block another key from entering. The adenosine receptors that caffeine occupies are not destroyed, they are temporarily occupied. As caffeine is metabolized, broken down primarily in the liver by the enzyme CYP1A2, with a half-life that varies considerably between individuals, but averages around 5 to 6 hours, the receptors it occupied become available again. The full downstream consequences of this adenosine receptor blockade, what happens in the various neural circuits that adenosine normally modulates, are not yet completely mapped in the scientific literature. What is clearly established is the mechanism of occupancy. The full cascade remains an area of ongoing research. The volatility of aromatic compounds, why some escape readily into the air above the cup, while others remain in solution, is governed by the strength of the intermolecular forces that hold those molecules to the liquid. Molecules that interact strongly with each other and with water tend to stay in solution. Molecules with weaker intermolecular interactions escape into the vapor phase more readily. The forces involved are called van der Waals forces, a family of weak, short-range attractions that arise between molecules whenever they approach closely enough for their electron clouds to influence each other. The magnitude of these forces depends on the size and shape of the molecule and the degree to which its electron distribution is polarizable, how easily the molecule's electron cloud can be temporarily distorted by a neighboring charge. Larger, more complex molecules have stronger van der Waals attractions to their neighbors and are therefore less volatile. Smaller, more compact molecules have weaker attractions and escape the surface of the liquid more readily. This is why the first thing detected above a cup of coffee, the aroma that arrives before the cup is raised, consists of the smallest and most volatile of the aromatic compounds, while the less volatile ones remain in the liquid and contribute to flavor rather than fragrance. The water molecule is worth examining at this level of detail because it is not a passive carrier. Its structure, one oxygen atom bonded to 2 hydrogen atoms at an angle of approximately 104.5 degrees, gives it a permanent dipole moment. The oxygen carries a partial negative charge. The hydrogen atoms carry partial positive charges. This charge separation means that water molecules attract each other strongly through what are called hydrogen bonds, an electrostatic attraction between the partial positive charge of one water molecule's hydrogen atoms and the partial negative charge of another's oxygen atom. Hydrogen bonds are stronger than ordinary van der Waals forces, and their abundance in liquid water, each water molecule forming on average about 4 hydrogen bonds simultaneously, is what gives water its unusually high boiling point, its high heat capacity, and its extraordinary ability to dissolve polar and ionic compounds. When water contacts coffee grounds, those hydrogen bonds are constantly forming and breaking at the molecular scale, water molecules moving fluidly through the porous cell structure while selectively interacting with the soluble compounds embedded in the cell walls. The extraction is, at this level, a process of hydrogen bonding and dipole-dipole interactions operating simultaneously across millions of particle surfaces. Unlike what many people assume, water does not simply flow through ground coffee and pass out the other side. Water molecules attach to the compounds inside the coffee, take what they need, release it, and move forward, a process that repeats millions of seconds every second. In a sense, water searches. It touches everything, binds, separates, moves on. Like a bee traveling from flower to flower, it never passes through empty-handed. Everywhere it goes, it does its work. The carbon structures that form the backbone of coffee's aromatic molecules are, at the atomic level, defined by orbital geometry. The carbon atom in an aromatic ring, such as the ring system in caffeine or in the pyrazine compounds responsible for roasted, nutty aromas, has its bonding electrons in a hybridized configuration called sp2 hybridization. In this arrangement, 3 of the carbon atom's 4 available electron pairs participate in the sigma bonds that form the ring structure, while the 4th electron pair occupies a p orbital that sits perpendicular to the plane of the ring. In a 6-membered aromatic ring, the p orbitals of all 6 carbons overlap above and below the ring plane, forming a continuous electron system, a ring of shared electron density that is distributed across all 6 atoms rather than belonging to any single bond between 2 atoms. This delocalization of electron density is what gives aromatic compounds their stability. The electrons are, in a sense, shared among the whole ring rather than pinned between pairs of atoms, and this sharing makes the structure more energetically stable than a comparable non-aromatic arrangement would be. The geometry is precise: bond angles of 120 degrees, a planar ring, and above and below it, a flat disk of shared electron density hovering at a fixed distance from the ring plane. One measurable consequence of this delocalization is bond length. In a simple carbon-carbon single bond, the kind found in a non-aromatic chain, the distance between the 2 nuclei is approximately 1.54 angstroms. In a carbon-carbon double bond, that distance contracts to roughly 1.34 angstroms because the additional bonding electron density pulls the nuclei closer. In an aromatic ring, every carbon-carbon bond measures approximately 1.40 angstroms, precisely between the 2. This intermediate value is not an average of alternating single and double bonds. It is the result of true electron delocalization. All bonds in the ring are identical. All carry the same intermediate bond order, and the 1.40 angstrom length is the geometric expression of that shared electron density.
every aromatic compound in the cup, every pyrazine, every furon, every ring in the caffeine molecule holds its atoms at this precise distance. The heat stability of caffeine, the reason it survives roasting intact while chlorogenic acids degrade and trigonylene is converted, is partly a consequence of this aromatic stability. The two rings in the caffeine molecule are both aromatic in character, and the delocalized electron density distributed through them makes the bonds within those rings resistant to thermal disruption at roasting temperatures. It would take considerably more energy than a roasting drum provides to break those delocalized bonds. Contrast this with the ester bonds in chlorogenic acid, a single bond between an acid and an alcohol component, held together without any aromatic stabilization, and the difference in heat stability becomes structurally explicable. Ester bonds are more readily hydrolyzed by heat and water. Aromatic ring systems hold. At the temperature of a cup of coffee approaching absolute zero, which is, of course, not achievable in practice, but worth considering as a conceptual endpoint, the atomic vibration within every molecule in that cup would slow toward its minimum possible motion. At absolute zero, the thermal energy that drives molecular movement would be almost entirely absent. The atoms in every aromatic compound would sit at the lowest possible energy state in their bond geometry. Still, at the precise distances from each other their electron configurations dictate. The arrangement would be fully defined by structure alone, by the angles and lengths of the bonds, by the geometry of every ring and every chain. Coffee's extraordinary chemical complexity, the 1,000+ volatile compounds, the interacting acids and alkaloids, the suspended oils, the dissolved melanoidins, would be present in exact molecular detail, perfectly still, waiting for energy to return and set it back into motion. At room temperature, those atoms are already vibrating. Every bond in every molecule is stretching and bending at a frequency determined by the masses of the atoms involved and the stiffness of the bond connecting them. These vibrations are not random. They occur at specific characteristic frequencies, which is why infrared spectroscopy can identify compounds by the frequencies at which they absorb infrared light. Each bond type absorbs at a predictable frequency, and the spectrum of frequencies absorbed by a sample tells a chemist which bond types are present. A detailed infrared spectrum of roasted coffee resembles a densely annotated document. Peaks at the stretching frequencies of CH bonds in aliphatic and aromatic systems. Peaks at carbonyl stretching frequencies from the hundreds of carbonyl-containing compounds. Peaks at hydroxyl stretching frequencies from the acids and phenols. The spectrum is effectively a fingerprint, a record of every bonding environment present in the sample, expressed as a pattern of absorbed energies. Two beans from different origins, roasted to the same degree, produce spectra that are similar in their major peaks and different in their fine structure. The underlying chemistry shared, the specific detail distinct. A cup of coffee sitting on a table may appear perfectly still, but that stillness is only surface level. Every atom inside it is vibrating. Every molecule is in motion. Millions of bonds breaking and reforming every second. Coffee, examined at the level of chemistry, is one of the most active systems in an ordinary room. The scale at which all of that activity occurs is simply too small for our eyes to reach. What sits above all of that activity, the cup itself, the hands around it, the room in which it cools, is the level the examination began at. The coffee in a cup has not changed its fundamental chemistry in the seconds since it was poured. The melanoidins are still in suspension. The acids are still in solution. The caffeic acid produced from the degradation of chlorogenic acids during roasting is still present at the same concentration it had the moment extraction ended. The atoms have not shifted. The bonds hold. What Chapter 7 examined, electron delocalization in aromatic rings, van der Waals forces between volatile molecules and the liquid surface, the constant vibrational motion at every bond in every compound, is still happening in the cup on the table. The molecular activity does not pause because attention has moved elsewhere. It continues at the same rate, driven by the same thermal energy, following the same rules. Beginning to zoom back out from that level of detail is not the same as leaving it behind. The atomic level does not disappear when the scale of observation changes. It simply becomes the foundation on which larger scale properties rest, properties that are now more familiar, more available to the ordinary senses, and that carry the same scientific content as everything that preceded them. The crema on the surface of an espresso, that pale, dense, aromatic foam described in Chapter 4, is, at the molecular level, a protein-stabilized emulsion of CO2 bubbles. Proteins from the coffee grounds have adsorbed to the surface of each bubble during extraction, forming a thin, flexible skin that resists the bubble's collapse. The same proteins that give crema its stability are part of what gives espresso its heavier body compared to filter coffee. They are present in brewed coffee at concentrations low enough to be invisible, but high enough to alter the texture of the liquid. The crema visible to the eye and the protein chemistry operating in the cup are the same phenomenon, described from two different distances. What the eye reads as a uniform pale brown surface is, at the scale of a microscope, a raft of gas-filled spheres, each one individually stabilized, each one containing a pocket of CO2 that the pressurized extraction forced into the water and that emerged as the pressure dropped. The color of a dark roasted cup of coffee, deep brown, nearly opaque in a standard espresso, translucent at the edges when light passes through a thin layer, is produced by melanoidins, those large, complex molecules built during the Maillard reaction. Melanoidins are brown because they absorb light across a broad range of visible wavelengths, reflecting very little. The specific wavelength distribution of what they absorb is determined by the same electron delocalization that governs the aromatic compounds discussed in Chapter 7, extended conjugated systems that absorb strongly in the visible spectrum. The color in the cup is electron behavior made visible at the scale of the eye. The precise appearance of that color depends on concentration. At the dilutions typical of filter coffee, roughly 1 to 1.5% dissolved solids by weight, The melanoidin concentration is low enough that the liquid transmits some red and orange wavelengths at its edges, producing the amber translucency visible when a cup is held to light. At espresso concentrations, 8 to 12% dissolved solids, the melanoidin population is dense enough to absorb across the full visible range, and the liquid appears uniformly dark, approaching opacity in a standard shot glass. The brown of coffee is not a fixed color. It is a concentration gradient, the same molecules producing different visual results depending on how many of them are present per milliliter of water. A very thin layer of espresso spread across a white surface would appear amber. The darkness of the cup is the darkness of density. The smell above the cup, the first thing that registers before the cup is even raised, is the vapor pressure of the most volatile aromatic compounds, each one present in the gas phase above the liquid because its intermolecular attractions to the liquid are weak enough that thermal energy at room temperature is sufficient to lift it free. The smell of coffee changes gradually as it cools. Why? Because the lighter, more volatile molecules escape first. As the coffee cools, there is less thermal energy available, yet the lightest molecules can still leave the surface. The heavier molecules linger longer. The smell of hot coffee and the smell of the same cup cooled are different from each other. They are simply two different moments of the same process, like the same piece of music played once in minor, once in major. The weight of a ceramic cup, the physical mass of it in the hand, the density that presses against the palm is mostly water. 98.75% water by the measurement cited early in this examination. The remaining fraction contains everything that was discussed across the preceding chapters: the caffeine, the acids, the melanoidins, the suspended oils, the dissolved polysaccharides, the hundreds of aromatic compounds in solution. The total dissolved and suspended solid content of a well-extracted espresso is typically between 8 and 12% by weight. In a filter coffee, it is closer to 1 to 1.5%. The difference in body, density, and aromatic intensity between the two brewing methods is, at bottom, a concentration difference. The same compounds present in different quantities per milliliter of water. A coffee plant produces its first fruit between 3 and 4 years after planting, depending on variety and growing conditions. The seeds inside those fruits, the green beans that will eventually be processed, shipped, roasted, and brewed, carry chemistry that began developing in the plant's metabolism long before the fruit ripened. The chlorogenic acids that are present at 6 to 10% of the green bean's dry weight were being synthesized by the plant's own enzyme systems throughout the growing season, accumulating in the seed as part of a defensive chemistry that makes the seed less palatable to insects and pathogens. The sucrose that will later caramelize in the roaster was being produced by the plant's photosynthesis and transported to the developing seed as an energy reserve for germination. The cell wall polysaccharides, the cellulose and gallomannan that survive into the brewed cup, were being laid down by the seed's own cells as they divided and expanded during development. Everything in the cup was built first by a plant through chemistry that required no heat above ambient temperature, no applied pressure, no human process of any kind. The roasting converted that chemistry into something it had not been. The brewing extracted a portion of what the roasting produced. The cup holds the result of those two conversions dissolved in water that served as the solvent for both. The caffeine in the cup has a measurable history. The molecule that exists in a brewed espresso is chemically identical to the caffeine molecule measured in a green Arabica bean from a different growing season, from a different continent, from a plant that was harvested before any of the equipment used to brew this particular cup existed. The molecular weight is 194.19 grams per mole in both cases. The two-ring xanthine structure is the same. The three methyl groups are attached at the same positions. Caffeine as a molecule does not vary with origin or roast level or time, only with concentration. The molecule itself is consistent. The melanoids in the cup are structurally complex and not yet fully characterized. The complete molecular structure of the melanoids produced in coffee roasting is still an active research question, which is unusual for compounds this extensively studied. What is known is that they form through Maillard reaction pathways from amino acid and sugar precursors present in every coffee bean of every variety. The melanoids produced in a Robusta roasted in Italy in the early part of this century, and the melanoids in a cup of Arabica brewed in a kitchen this morning share the same basic chemical architecture, built by the same reaction pathways from the same class of molecular precursors. If one of these details stays with you, the behavior of 2,4-furylthiol at parts per billion concentration, the structural memory written into the crease of a bean, the way adenosine receptors wait patiently after caffeine vacates them, it may be worth leaving in the comments. The quietest observations tend to be the most interesting ones. The cup cools. The aromatic compounds continue migrating upward, each one following its own vapor pressure curve, the most volatile leaving first. The temperature in the liquid drops in the same manner it always has, surface first, interior last, the rate governed by the same thermal physics that governs the cooling of every warm liquid in every room where the ambient temperature is lower than the liquid's temperature. Nothing about the process is particular to coffee. What is particular to coffee is the specific collection of compounds that the cooling liquid contains, a collection assembled through the chemistry of a living plant, the applied heat of a roasting process, and the selective solvent action of hot water. What has not changed throughout this examination is the coffee itself. The compounds in the cup are the compounds that were always going to be there, given this particular bean, this particular roast, this particular water. The atomic structure of each molecule is fixed. The intermolecular forces operating between them are consistent with the same physical laws that have governed matter since long before the first coffee plant produced its first fruit. What the examination changes is only the observer's relationship to the cup, the scale at which it is held in attention, the depth at which its ordinary presence is followed. The cup still holds its warmth. Steam rises from the surface, and the chemistry inside continues. Good night. See you in the next video.